Okay, so returning now to the Poisson random scatter theorem that we discussed last time, and now trying to sketch out the proof and the logic underlying why this works. How does all this work? Because it's not, so it's not a given, I should say, that this would work in the sense that we've made a few assumptions. We made a few assumptions about how things behave, in particular that there can't be more than one hit in a given area. Okay. But and that not hitting and that non-overlapping regions are IID. Uh, when we make assumptions, it's possible that there's a process that there is no way to really describe the process that we're talking about. It might not make any real statistical or probabilistic sense. So we have to be careful about that, and that's why it's kind of a remarkable property here that when we make those assumptions, which in a lot of cases might make some sense, we actually get a process that we can do a lot with, because it's pretty tractable once we get it into uh, the Poisson kind of sphere of influence, or the world of the Poisson distribution. So just to sketch this proof, and let's think about how we might do this intuitively. So we have our region R, and let's just suppose R is a square for simplicity. It doesn't have to be, but this is why we're sketching the intuition. If we wanted to prove this in full generality, we wouldn't be able to make this assumption, but it's a convenient assumption in this case. So here's our square, and we're going to subdivide our. Let me make a few copies of this. Okay. So we're going to subdivide R into subsquares. So really didn't give myself much room to work with here. All right, let's move this. Okay. So we're going to divide into subsquares. N equals, let's say, 2 to the 2, 4 to the 2, 8 to the 2, and so on. So, and we're going to count N sub N is going to be the number of subsquares with at least one hit. Okay. So we're going to start off, we're going to say, okay, I mean, we could start off with just the square itself, N equals 1 to the 2. Okay. But let's not, but what we're actually going to do is, it's like you're cutting a pizza, but it's a square pizza. So you do one cut here and one cut here, right? Oh, okay, bear with me. Okay, so let me lay down a pattern first. And I want the pattern to be exactly the same in each of these squares, because this is really just, these are identical copies of the process. It's just a question of how I choose to analyze the process. So I'm going to draw the lines as, we'll draw red lines. And so first I'm going to subdivide as, that's terrible. I don't want to put one in. It should be theoretically impossible to get rid of this one and make it more obviously here. Okay. So theoretically, it's impossible that a point would fall into two regions because it's a zero-dimensional space. Okay, so here I do this subdivision here. And given that I have 4 regions and my number, my size here is n sub 4, right? When I have 4 regions, in this case, there are 3 subregions that have a hit, right? This one, and this one. So there's 3 out of 4, but we don't count the 4. We already know there's 4 total. And then we can go here, and what we do is we continue to cut the pizza, meaning every square then gets cut into 4 additional pieces. So we cut this here, we cut this here, we cut this here, and we cut this. Jeez, this thing's showing up in the middle of my, always in the middle. Anyway, it's not that important. Oh, geez, no, I can't move that. It doesn't matter. Okay. So now what happens? So what happens when we do this is the count becomes, well, it's n4 squared, n to the 16. I should write, n2 squared. How many regions are there now that have a unique point? Well, there's this isn't the illustration I wanted. I wanted this. Well, it's 5. It's just, it is what it is. There's 5. So then I would continue to do this progressively. And you can see that it's going to take a while to demonstrate if I continue, but what I'm going to do is keep breaking this up into pieces. And in this case, there's going to be 64 regions, 8 squared, right? So this is n equals 4 squared, n equals 8 squared. And this is still going to be 5 because there's only 5 points total. So once you're continuing to subdivide, you eventually get to the point where you trap each point into its own square. And that's the whole idea, right? That's the whole idea, is that as n increases, so does the number of points that we have in unique boxes. And we can actually see that as n increases, the number of boxes with a point actually just converges to the number of points, because we're going to eventually trap each point, and that's by assumption 2. So assumption 2, remember, told us that there are no multiple hits. So we know that we're going to trap each hit into a box, and eventually everything's going to get compact to where the box is barely bigger than the size of the point. And since there's no multiple hits, it's impossible to have more than one hit in a given box, because they would have to basically essentially fall right on top of each other. Okay, so then for each for each value of k, 0, 1, 2, etc., the event that the number of boxes containing a point is bigger than or equal to k increases to the number of total points in the region being bigger than or equal to k as n increases to infinity. It's a monotone, so it's a monotone it's a monotone event, meaning as we increase n, the event only gets bigger and bigger, right? The possibilities of the event happening only gets bigger and bigger. And so what that tells us is that when we take the probability of this, so the probability that the number of boxes is bigger than or equal to K. Well, there's a property of probabilities that we did not go through yet, but if we have events that are nested within one another, we can actually, this is related to the rule of differences, actually, that these probabilities will actually increase up to the probability that the number in the region is K. And by the way, I understand that this proof is maybe above, this may be above your head, depending on your level of math preparation and where you come into this course. And so it's important to understand that this is not, I should have colored these, by the way. That if you think that this is a bit much right now, that's, there's going to be parts of this course that are like that. But it doesn't prevent getting some intuition, right? So it's important to still pull intuition out of these as the course kind of goes from, we kind of go back and forth between technical, conceptual, and we try to build our intuition in that way. Okay, but the idea here, the point is that if this is true, then we actually can conclude that the probability that n, the number is exactly equal to some value, gets closer and closer to the probability that the number in the region is in the total region is exactly equal to some value for each K. Okay, now why is that relevant? Why is that important? Because by the third assumption here, independence and homogeneity, we didn't write it here, but the number n, if we define this as the sum from j equals 1 to k of these indicators, which we've assumed to be IID, their IID, 0, 1 valued random variables, they're IID Bernoullis, which means they are, in fact, their total, their sum is a binomial, K trials, and some probability P. And that probability P is unknown as of where we made this assumption, but it's going to have the binomial distribution with K trials and some success probability. And that success probability can be determined from what we've figured out, what we've assumed down here. Okay. But we'll leave that and we'll derive that actually as part of this proof. So by assumption 3, n sub n is binomial n and p sub n, where p for some p sub n. Okay, we don't know what p sub n is yet. But we can figure out what p sub n is because we know that the number in each box is Bernoulli. So the mean mu sub n of which is the expectation, we're defining that to be the expectation of n sub n. N sub n is the sum of the boxes, so it's n, it's the independence and homogeneity assumption. Whatever the probability p sub n is, p is, and some p, right? This tells us what? That the expectation of n by the binomial must be k times p, whatever p is, right? In this case, we have n total trials and p sub n, so it's n times p sub n. So we're going to define, and then we can define mu to be the limit of these mu n's, right? Right. This here, this mu sub n is increasing with n, so it has a limit. And therefore the limit exists, we can define the limit to be mu. Okay. So because of this, um, so how would we see this formally, just to be clear? So the mu's are increasing, so mu n are increasing with n, right? And so the limit of the mu n exists. And also mu n converges to mu by definition of mu, and mu is finite by assumption. But suppose not. So suppose not. Suppose this is not the case. For a contradiction, suppose that mu n converge to infinity, and let q sub n be defined by 1 minus p sub n. Then in this case, sigma n, which we define as the variance of n sub n, remember n sub n is binomial n and p sub n. So what's the variance? It's n p sub n q sub n. Because p and q are less than 1, less than or equal to 1, we can bound this above by n p sub n. Okay. Which n p sub n is equal to mu sub n, right? So therefore, this tells us that sigma n squared divided by mu sub n, well, sigma n squared is less than or equal to mu sub n. And we're assuming that mu sub n goes to infinity. So this ratio converges to 0. Okay. Therefore, for each k and all large n, what happens? Okay, so what's going to happen is the region mu sub n minus 2 standard deviations, right? So the region, the interval within 2 standard deviations of mu is going to be completely to the right of k for every k. So the way it's going to look is like this. So we have our region, we have a value k, any given k. We have mu sub n, which we've assumed for contradiction is going to go to infinity. And we have mu n minus 2 sigma, mu n plus 2 sigma. Okay. So this is the region we're talking about. And because sigma n over mu is going to 0, this region is going off, right? It's kind of going off to infinity, and the region is bounded. So then this is where we can apply Chebyshev, right? Chebyshev tells us that the probability that n sub n is less than k is at most a quarter. And then the probability that n sub n is bigger than k is at least 3/4. Okay. But because this holds, so this holds for all K, right? Since this holds for all K, the probability that the number in the region is infinity, which is equal to the limit on K, probability that the number in the region is bigger than or equal to K. Well, since that's bigger than or equal to 3/4, this limit is bigger than or equal to 3/4. So the probability that the number in the region is infinity is bigger than 3/4, which is of course bigger than 0. And that contradicts assumption 1. So the reason why this limit has to be finite is that the total number ultimately in the region has to be finite. And the only way for something to be finite with probability 1 is if its mean has to be finite if it's going to be finite with probability 1. Okay. So realize that's a long way to get to something that should be intuitively obvious. But this again, to prove these things in full detail, it requires that kind of, we have to get into the weeds a little bit sometimes. So that tells us then that the limit of these finite averages goes to a finite limit. And in order for that to happen, P sub n has to be going to 0. The probability of falling into any given box as we shrink the sizes of the box has to be getting smaller and smaller. Okay. But now we're in the situation where we have the binomial approximation theorem. So remember the Poisson approximation to the binomial says if we have independent or approximately independent, in this case, we have approximately independent Bernoullis with same probability with n going to infinity, Pn going to 0, n times Pn going to something finite, then what happens is that the probability that the number in the region is equal to K, well, by the way we've set it up, we've said that this is equal to probability that the number in each of these, the number of boxes containing at least one hit is K. We know that that limit is e to the minus mu to the K over K factorial by the binomial approximation. So this is telling us then that the number in the region, the total number in the region is Poisson with parameter mu. So it would remain for us to show that the last thing we need to show is that non-overlapping regions are independent. And Poisson are independent Poisson with given intensity. So the intensity lambda times the size of the region. So for this, we can use a similar argument. So use a similar argument. So what is the similar argument? Use a similar argument to say that take B, a subregion of R, and then in this case, we can always write R to be B union B complement. So this is a disjoint union. Okay. So if we were to cover R with boxes, like we did above, then we can let number of B sub n to be the number of boxes that are in region B at time n. So at level n, where we're, so, you know, if B, if this is B, then we will slowly be removing boxes. Well, we'll be fitting a specific number of boxes into B as we refine this partition of R. So if that's the case, then we know that the number of hits within region B at time n is going to be binomial. The number of trials is the number of boxes that are in B, same probability P sub n, right? Which we know that is going to be approximated by same thing. It's Poisson. And the intensity now is number of boxes in B Pn for each time n. And then what we're doing now is we're going to converge this. So we consider taking this n to infinity. So number of boxes in B at time n times Pn. We can rewrite this by multiplying and dividing by n. Okay. Number of Bn. N, remember, is the number of boxes in all of R n's, in all of R. So this is another way of writing the number of boxes in all of R is number of Rn using the same notation, n times Pn. Well, we know that n times Pn converges to mu. And the ratio of boxes in B to the ratio to the number of boxes in R actually turns out to be the ratio of the areas of B, area of B to the area of R as n goes to infinity, right? And so in this case, the number of points that occur in B is Poisson ratio of area. So how big is B compared to R times mu. That tells us that mu, I'm sorry, we can define lambda as mu divided by size of R, and we would be done at that point. We would complete the proof. So what have we done here? What is the logic behind this? The logic is that we're trying to derive a pretty powerful and a pretty general theorem, and what we're doing is we're building it up from Bernoulli random variables, incidentally, right? And so we're just finding a clever way to write a relatively complicated number, complicated random variable, and express it in terms of very simple random variables, which are Bernoullis. And then they're independent Bernoullis, and we use the Poisson approximation theorem. So it shows you how we can really go far with this as long as we know how to put all the pieces together. So this is the Poisson random scatter theorem. Poisson processes in general have very interesting properties. All of these properties pretty much derive from properties of the Poisson distribution itself. And we're going to go through a couple of those properties in the next couple of videos.